Okay, welcome back. Let's take a look at statically indeterminate torsion. So we've already talked about torsion and twisting and angle of twist. Now we're going to do a concept very similar to what we had in axial loading. So you might remember axial loading, and I want to say the example we had looks something like this, where there was some collar on there. It was pinned on both sides, and we put a force on here, and we had to say, what was the reaction on those two sides? Some was taken up by one side, some was taken up by the other. Same idea here. If I had this tube or this I don't know, rod or whatever it might be, and I'm putting a tension, meaning I'm twisting somewhere, not quite in the middle, closer to B than A, there's a reaction. There's a reaction at A, there's a reaction at B, and but they are not going to be the same, and it's not all on B and all on A, but instead it's somewhere in between, right? So how do we get there? Because we have one equation from statics. Our equation from statics would say that the tension, or sorry, the torque at A plus the torque at B has to equal the torque at C, or TA plus TB minus TC is equal to 0. That's kind of using the right hand rule type of thing. I guess technically what it would be saying is this is my positive direction and that's my positive torque. No big deal. Just the key is that that they have to equal out, right? Some on one side, some on the other. So I have two unknowns. This would be a problem where TC is known. I want to know the reaction at A and B. Well, how do I get there? I need a second equation. That's where I can break in this new concept of angle of twist. So I have an angle of twist from A to C, and I have an angle of twist between B and C. Well, that angle of twist has to be the same because this material doesn't separate, right? So this distance rotated has to be the same on either side. So that's what we're using for our next equation, this idea of angle of twist between AC has to be equal to BC. Well, we learned last time our angle of twist is TL over JG. So putting in our variables, our length on one side is 2L over 3, on the other is L over 3. And then these are just variables, of course, so it makes it easier to cross things out. But say we have the same J and the same G. That's the same modulus of rigidity J and the same polar moment of inertia G. The JGs will cancel out, my L's cancel out, and I get a relationship between TA and TB. And I see that TA, 2TA is equal to, or less a little bit there. It's supposed to say TB. Oh, let's fix it right now. Oh, right there. So, and that might even make sense to you if you were just to examine this thing. The reason that is the closer I move to B, the more load B will actually be supporting. So, because it's like I have to get that same angle of twist, but I have less room to do it on. So if it were really close, I would really have to be twisting a lot. But if it's really long, it doesn't take as much. So the closer to the side, but that's neither here nor there. It gives me a relationship between TA and TB where TB is twice as much as TA. I think that's the way to say it. Sub that into my equation 1, which is the statics, and I can solve for the 2, and I get TA is TC over 3, and TB is 2TC over 3. So that's kind of how you do it if you had a single force in the middle of a pipe. This one is much more common. So I decided to do a longer drawn out example here where I have a composite shaft, meaning this is similar. We had an exam problem similar to this with steel and concrete, and we had an axial load. Well, instead of axial, now we're saying we're twisting on it, and it's like a cantilevered pipe, right? So we have a steel tube with a 1-inch outer diameter and a 1/2-inch inner diameter. How do I know 1/2 inch? Because I have a brass core with a 1/2-inch outer diameter. So just easier to write it that way, right? So let's see, steel has a modulus of rigidity, 11.2 times 10 to the 6, brass, 5.6 times 10 to the 6. We want to know the maximum shear stress in each. And as shown in the drawing, as you can probably see, with this torque of, that's not even given in here. This should be under given, right? Given the torque of 250 foot-pounds, getting sloppy here. If I do provide that torque, the angle of twist, which I'm showing up here in this phi, has to be the same for both, right? It doesn't matter how far I'm out, it's still the same angle. So so that means that just like I just saw, I have two equations. First, let's start with our statics. The statics would tell us that the torque in the brass plus the torque in the steel must be equal to 250 foot pounds. That's our statics. That gives us our first equation, which I'll call 1. And the second is this compatibility condition, basically that the angle of twist is the same. Compatibility. I hope I spelled that right. So from compatibility, I know that the angle of twist in the brass is equal to the angle of twist of the steel. So that means I have T brass times the length of the brass, which I'm just going to write as L, that 4 feet. I have J brass, G brass must be equal to T of the steel, length of the steel, which is also 4 feet, J of the steel, and G of the steel. And I see that the length is the same at this 4 feet. So I'm just going to cross those two out. And then I'm going to start subbing in my values to get this relationship. Well, let me do it the way I did in my notes. It's a little cleaner. What I did is I said, let's go ahead and find the torque on the brass. And so just moving the J brass, whoop, that's a B, G brass to the other side, divided by J steel, G steel, times the torque of the steel. And I've actually seen other people work this type of problem where they say, well, really, it's always just a ratio. You're always just looking at the stiffness ratio or the ratio between the J's or the ratio between the lengths. And that's true. So, but regardless, I think it's easier to write it out this way. All right, now let's put in our values. So what do I have here? Remember the polar moment of inertia, we have pi over 32 times the outer diameter. This is the brass, so its outer diameter is 0.5 inches to the 4th power. And then G brass is given, right? G brass is 5.6 times 10 to the 6th. And I'm going to divide all that business by, I have pi over 32 times 1 to the 4th minus that 0.5 to the 4th for my polar moment of inertia. And then I have 11.2 times 10 to the 6th for my modulus of rigidity. And then, of course, this is my T steel over here. Make that just a little bit longer, something like that, right? So what I do is I end up, if I put that in my calculator, right, I got T brass is equal to 0.033 T steel, a very small number. What is that actually saying? It's actually saying that let me write the little equation number 2. That's saying that the brass takes hardly any of the load at all. Really, it's the steel. And that's because steel is stronger. It's also much wider. It has a much larger modulus of rigidity because it's a bit bigger diameter. But regardless, we don't care about that. So we have our second equation. We are going to sub that into equation number 1. And if I do that, then I have this 1.033 T steel is equal to 250 foot-pounds. That gives me a T steel. If I divide that through what I get, 241.94 foot-pounds. And then from that, I can plug that back into that equation number 2 to get the brass is only 8.06 foot-pounds. And those sure as heck better add up to 250, and it looks like they do. But that wasn't the question. What is the question? We're going to find the max shear stress in each. So there is one last little bit, which is what can you tell me about the stresses, right? Because we just found the torque. So the last little bit is we know that the stress, the shearing stress, I'll start with the steel, is equal to the torque in the steel times the radius of that divided by the polar moment of inertia, which would have been better if I calculated from the beginning since I have to keep doing this, but whatever. 241.94 foot-pounds for my my torque. And then I want that in inches, so I'm going to multiply it times 12 inches. I could have done that earlier, but whatever, doesn't matter. C And that's why I want to do this is only half an inch, right? It's that radius. And because the diameter is 1, take half of that. Polar moment of inertia, pi over 32, once again, times the diameter, which we said was 1 to the fourth minus 0.5 to the fourth. Let me do just a quick little rearranging to give myself a little bit more room, make it a little cleaner, put it on one line. And I ended up with 15,772. My units here would be PSI because I am working in pounds and inches. And I know stresses are in a force over area, right? So that I might as well put a box around that since that's like a final answer for my torque of the steel. Sorry, my shear stress on the steel, my shear stress on the brass, same idea. I have torque of the brass, C of the brass over J of the brass. We found the torque to be that 8.06 foot-pounds. Once again, multiplied by 12 inches per foot. For that little conversion, what is my radius of that? I have 0.25 inches because the diameter is 0.5. And divide that by this pi over 32. Its diameter is 0.5 to the fourth. And from that, I end up with 3,943 PSI. So there's my oh, pretty ugly, but it works. Yeah, so that's basically the process. It's not overly difficult, kind of a cool little concept. It just builds on this axial bit, but now we have rotation in there. So give the homework a shot, or hopefully you learned something from this video, and I will see you all next time. Thanks for tuning in.